Hello, welcome to today's interactive session. We'll wait for a few minutes and then we can start. If you have doubts, you can start discussing those doubts. I guess you can, if you have any doubts, you can discuss. So I have a notebook on using character level arguments. If there are no doubts, you can just go through that. Else you can discuss the doubts first and then you can go through the notebook.
Good evening, good afternoon, sir. I have
And
doubt.
yeah,
Actually, whole of last was very difficult
okay. So,
because
uh,
from the
huh,
beginning, if it I missed understanding something, then the whole lecture, the later it was difficult. Uh, it could be a really lame question, but
huh,
somehow like in the RNN. Basic the first slide of RNN itself, I did not understand how the information is uh, going. I mean, there is U, there is V, and W. I
yeah.
can understand U, I understand W. This something is V is also going, and then how W is happening, I did not understand.
Oh, okay. So, fine. Okay, let me connect with my iPad. Give me 2 minutes.
So if you open the lab, I will have to rejoin after you open. Let me see.
Are you able to see my screen?
Yeah, I can see.
Okay. Okay. So the basic structure of RNN is this, right? So you have some input here, X,
Mm,
and you have some network. We still don't know what that network is. It may be a multi-layer network or some neural network to do the computation of this. So because this is an input layer, this is an input that you have. Uh, this is
mm,
the input that you have, and this is another layer. So you have to use some weight function here, right? So that is how neural networks are created. So here we represent this weight matrix by say P.
mm,
And suppose we're not talking about sequences, we'll have some output layer here, and so this is, let us say, the output that we have, say Y. And so for going from this to this, you have another weight matrix, say P. Now because so in the lecture, we, I think it was mentioned that we want a network which performs the same function for any input that we have. So that means this whole function that you do, this should be in a sense repeated across all inputs that you have.
mm.
So let us take the example given in class. Say you have to say generate the word tea, right? You have to generate this word, and so first of all, what do? You have D as an input, and you multiply this D with some matrix Q, and your task is to generate or predict the next word, right? And so
Mm,
you output E, and you do this by multiplying, sorry, you multiply phi here. So now this E must be given as an input to the next layer, right? So ideally you want something like this. So you want this E to go here. So probably it will be multiplied by this because you are repeating the same function again.
Yeah, that I mean, this is going to you that for to the next word
Hmm.
that was in like 12th week, the last lecture. This is how they showed.
Yeah,
But in that first RNN, this was not like there is one going from in
yeah, that is
between.
also there.
There is
Yeah, yeah. Hmm. So I'll come to that. So this is
okay.
a simple version that you just give your input and you generate the next word E, and again this will go here, and we have E, and then we generate E. So the RNN, so this is a simple thing, right? You see one
Mm,
input, you predict the next word or next character, use that character as an
mm,
input for the next sequence or next time step, and then you go on. So the RNN, for RNNs, what it was decided that okay, instead of sharing this as the input, why not share the state space? So by state space, you mean what is, so whenever you see D, your models will have learned some weights, right? Your models will have learned some
mm.
weights. So
Yeah.
that means your model is at a particular state, you can say. So I see
Mm,
D, my model is at a particular state. So the model knows that I have seen the letter D and it should predict the letter E. So let us see what this state means if you have two different, uh, I mean, so suppose at this step, and so let me say this is time step one, this is time step two, this is time step three. So at time step S1, the model sees D as the input, and it knows that it has to output E as the output. At time step 2, the model sees E as the input and it outputs another E as the output. And at S3, the model sees E as the input and outputs P. So if you look at S2 and S3, you can see that even if the model sees the input as E, the outputs are different, right? So that means the model has some information about what was seen before that. So at S2, the model knows that it saw D before this, but at S3, it knows that it saw another E before that. So that means based on what or how the models have been trained, it has a uh, corresponding state space. State space means that how do you, what is the state of the system or what is the state of the data that is coming in. And based on that,
Mm.
you need to uh, train your network. So that means instead of passing this output here as an input, because if you just pass E here and E here, this should give the same output, right? Because upon seeing E, you need to output E, but it also means upon seeing E, you need to output P. So this does not make sense. If there is a neural network and you give the same data point, but you have two different labels, say for E, you can output E for E, you can output P as well. So it will not learn anything. It will be confused, like what does E even mean? So instead of passing the E as an input, what you do is pass the state as an input. So it basically says, okay, I have seen these letters here. What state is my input or what state is my network, and based on that, the network will make the decision so whether it wants to output E or whether it wants to output P. So that means instead of giving this E as an input, you pass the state. So whenever you train the network, this will be at a certain state, right? So this is at a state S1, this is at state S2, and this is at state S3. So even then, the state has to be learnable, right? You cannot just say that, okay, if I multiply D with U, I get some S1, and of course, I do a nonlinearity here. But even then, the state should be learnable, right? Because the state S2 should know that when it sees E coming after D, it should output E. So S3 should learn that when it sees E coming after E, it should output P. So because it is a
Mm.
learnable thing, how do you learn? You make a weighted connection here. You give some weights here. So basically that that becomes the input to the next step instead of the exact input or output of the previous step time step. So is the intuition clear?
Yeah, that is, yeah, yes, I'm a little bit understanding. So
Mhm.
now I understood that how like the state formula is given as ux plus sigmoid of ux plus wsi minus 1 at
Yes.
state
Mhm.
I.
Yes.
So okay, that and what happens in this y. So there is another bias, different bias taken for V, and then there is a single bias taken for this state. I
Uh,
mean, when this formula was given in the, and then the
mm, yeah.
Saraz, like you guys understood, say everyone understood, yeah. I was like, no, but how? So there is it says that ux plus wsi minus 1 plus b. I
Yes.
got it. So they are taking, there is, the bias is not considered from in initial at u, that there is no bias considered, I
Yes.
guess.
Mhm.
And then there is directly just one bias, or maybe it's a combined, just written for whatever. I got it. Then
Mhm.
there is yi equals to the output function of vsi plus c.
Mhm. So you are saying. Why are B and C
So
different?
no B and C different. That is also fine. Then
Uh,
yi is a function of xi s w u v.
yes.
Now, how yi is a function of where did w come? I mean, there is no I mean, how does that
So
working?
so yi is a function of si among other things,
How
and eh,
no
yeah,
okay, because si is
ah,
written as
si is a function of w, some
that.
function of among other things w.
So I did not understand. Like you are calculating si after you get. That's what I did not understand. Uh, SI is come. I mean, if you can open the first slide of
Mhm.
that lecture,
Okay.
the diagram is, yeah.
Let
So I
me
just
see.
wanted to know like SI, uh, how that SI is. Is it after, before?
Is this visible?
Yeah, it is visible, but
Yeah, yeah.
before this. Okay, okay.
This one.
Yeah, anyone is actually fine. Now, if
Yeah.
because here S is not made, even go for the before. Explicitly, it is not, S is not mentioned here, and is the first one probably, oh, it's not mentioned.
I think this is the first time.
Yeah, this is only. Okay,
Ah,
if you can see that uh, when you're when you say that after you giving X as input and
yes.
your pre-activation will be UX plus
UX.
whatever by, yeah, you just let it be UX,
Yes.
and then you're taking UX
And then we're
uh,
doing sigma of UX.
sigma of UX,
Yes.
and then that sigma of UX is passed for the pre-activation in that where the W is written. So
Yes.
you write sigma of ux plus, so it is actually sigma of ux plus wsi.
You are
And
saying that sigma is applied only on UX and plus WSI. Are you saying that?
yeah, that's what, like first is,
Okay.
yeah, first suppose you're taking or right now the sigma is, I mean, it's you're just taking linear ux from,
Mm,
so first step is here you're getting ux.
yes. There is another. It's not. I was thinking there was another one.
Oh, okay, okay, there is one s given. Can you just go back? Yeah, here, yeah, this one, this S1, S2, S3 is given,
Mhm.
or S1, S2 is also,
This one.
one is also fine. So
Mm.
S1 is equal to, I mean,
UX
forget about
sigma of
W for
UX
now.
plus. Yeah.
S1 is equal to sigmoid of WX or sigma WX, whatever.
Yes.
We can do the sigmoid later. Yeah, here it's written, UX plus B.
Yeah. Yeah. Okay.
So
Go on.
then how Y is a function of W?
Oh, so in this case, we're still not doing the. So this is a very vanilla setting, right?
Correct. Here we have not done the connection. So when
Yeah.
we do the connection, also how is that connection happening? Like
Okay.
because
So when we are giving the input, so we are not just giving X as the input, right? We are giving X as well as the state as the input. So instead of X, we will
but
have
that
X
state is
comma
going.
S.
That is for the next word that is going. But
Hmm.
for the top, my input is UX only. No. For
No,
UX,
so take this
when
example
it's
like
going to the Y, yeah, when it is going to Y,
ah
how it is written, it is correct. Y in this case, Y is written as VSI plus C.
yeah, right. So
VSI plus C,
ah,
that I understood. Then
yeah.
they said that Y is a function of W. How?
So take this example. So suppose we are at y2. So why does what does y2 depend on? It depends on v. It depends on this blue box, right? This
Hmm.
blue box, and this blue box gets
Oh, this blue
input.
box is
Yeah,
coming from the previous one.
yeah, right.
Okay, okay.
Gets
Oh,
w, it
okay.
gets y, it gets x.
Oh, okay.
Is
Okay.
that clear?
Yeah, yeah. Oh, thank you.
So for first y1, we don't have s0 explicitly. So then we
Hmm.
just say we make it zeros or we just
Yeah,
randomly
in
something.
the today's lecture, they said that instead of that, that also is like a kept as a parameter.
Yeah, yeah, that it also can
Not
keep it
about.
as a learnable thing.
Okay, rest I have to afterwards study more. Then only I'll
Okay.
get out.
Yeah, any more doubts? Any more questions? Okay, then we can, I think, look at the notebook and
Yeah, I mean, right now I don't have doubt.
yeah, so
Yeah, yeah.
so is this notebook visible?
It's visible. The font is too small.
Okay.
Yeah,
It's
it's
fine now?
better. Yeah, better. Yeah,
Okay.
yeah, yeah, yeah. Thanks.
Okay, so I have taken this notebook from the PyTorch tutorials, and here will be, so before going to this, let me show you the data set. So this is the data set that we have, and the link is given here. I'll also share this notebook in the drive, shared drive. So basically, you have a set of names, like say, suppose I click on Scottish, and this data set contains all the Scottish surnames. Or if I say I have this Chinese file, and then it contains all of the surnames for Chinese people. So, oh, okay, Shyam Sundar is, are you able to see now? Or if you're having issues, you can reconnect. I think there is some bug in Teams. You can just reconnect and see if you're able to see the screen. Let us wait for him to connect. Yeah, are you able to see this? So the task that we have here is given a name, given a surname, you want to predict whether that surname is, say, English or German or Chinese and so on. Applications for recurrent neural networks. Okay, so for this, you have to download a data set which is given here. So the dataset link is here. You can just go to it and it will download the dataset to your drive to load your Google Drive because you are using space from your drive. You have to give them permission to look at your drive. So these two lines are important whenever you are trying to load data from your drive. Okay. And now there are some certain pre-processing that you have to do. So these these are just yeah this will be shared there. You can download it. So instead of this line that I had here, so I have shared my data here. You can just paste the link where your I mean your local link here instead of my link. So this is a piece of code to write or read the data. So so as you saw, the data set contains just names, no comma, no full stop or anything. So you have to uh, convert your data to ASCII because that is how the system will understand your code. And for example, you because say this is a non-English surname, maybe this is Slovenian or something. So there are these special characters like S with some prime on top of it, and we the English or even the system don't recognize these characters. So it's you have to convert it to ASCII format, and this piece of code does that. There's just 2-3 lines of code, and then because this is a classification task, you have your surname, and your task is to classify which this country this surname belongs to. So let us run this code. So again, you have to download this data set, which is given here to your own Google Drive space, and then paste the link of that space to wherever this thing is there. Okay, so as you can see, this S and A just special characters instead of that it has been converted to just S, E, S, or A. So now let us see some examples. So I take I've taken the French language, and I'm just saying what are the top five or the first five um, star names that are given in the French file. So these are some of those: Abel, Abraham, and so on. And now, of course, you cannot use these characters as input to your model. So that is what we've been looking through till now. So one of the nice thing that we did was, or that we saw we can do was just one hot input vector that you have. So that means whenever you have a, so you have a 26 dimensional uh, vector, and in place of a you place one, and rest of these are all zero. So here what we do is we index find the index of the letters, that is a is 0, b is 1, c is 2, and so on. Then we convert these to tensor, because this is a PyTorch code after all, and we have to give tensors as input to PyTorch. And then we convert each of the lines, or each of the lines that we have there, to tensors. So we have a, b, e, and 4 cross, say 26 dimensional representation for each of these letters. So let us do that. Yeah. So here what we see is we are printing the letter to tensor, or the one hot encoding of the letter O. So O is at, say, this distance. And then what we're doing is similarly we are applying this to all of the characters, or all of the letters of the word Jones. So this is the encoding of the word J, this is the encoding of the word O, this is for N, and so on. So now this is a sequence to sequence, oh sorry, this is a sequence learning problem. So you are given a sequence of characters. So your character, so for this example, the sequence contains the characters J, O, N, P, and S. And uh, your task is to classify at the end. So again, I think you have seen this example, but can you give me an example where you are given a sequence of words and your task is to classify something at the end? So here you are just seeing a class sequence of characters. So suppose you have a sequence of words and you have to tell something about it. So anyone? Okay, so there is this problem called sentiment classification. So you must have seen this in Amazon reviews, right? Given a sentiment, you just say what is the sentiment regarding a product, whether it is a positive sentiment or a negative sentiment, or so on. So that is one another task where you are given a sequence of words, and based on the sequence of words, you decide whether it is a positive sentiment or negative sentiment, and so on. Okay, that's just an example. So now let us create the hidden network, or sorry, the RNN network. So again, this time we'll be using RNN, but as I mentioned in the previous lectures, we will have to import this NN module class, because it contains the definition of how to create neural networks. So this hidden size is the size of the state Si. So you have this Si, which is multiplied with the matrix W. So what dimension do you want Si to be in? So you can think that uh, X, the input will, what is the size of your input, right? So here the size of your input is, say, 5 times 26. So there are 26 of these and times 5. But so this is a hyperparameter. How much how many dimensions you want to keep to, so that you learn the space, hidden space. Okay, so as you saw in RNNs, what are the inputs that you get? You get X, and you get the hidden state from the previous time step, right? But how do you how is it possible to combine these two? So one possible thing is to just add these up. You have the input x and you have the hidden set si minus 1, and you just do si, uh, sorry, you just do, sorry, I'm not adding this up. I'm adding the size. So suppose my input is say 26 into 5, which is a 130 dimensional vectors. And suppose my hidden state is, let us say, 100. So because how do I combine those two and give it to the next step? I just concatenate this. So by concatenation, I mean I have so my input was 130 dimensional, and suppose my hidden state is 100 dimensional. So overall, I'll have a 230 dimensional vector, where the first 130 dimensions will correspond to the input that I'm getting, and the remaining 100 dimension will be the will contain the representation of the state space. So that means you are just placing the state information below the input information that you have. So that is why we have defined it as a simple linear layer, which whose input is of size, input size plus hidden size. And now once you have this input plus hidden size as your input, so that your next step is to again go to that blue box, if you remember. So that means if you are going into the blue box, that means you are learning a new state, right? And we have fixed, say we know that the hidden state will be of 100 dimension. So that means you are going from this concatenated input to again the 100 dimensions that you have. And this is your how your W matrix, W and P matrix, sorry, U and W matrix will multiply to these layers. And similarly, now you have to go from the hidden state to the output state. So output state, you know, right? So suppose you are doing a character level prediction. So that means you will have a softmax over all possible characters, and which will give you the probability of seeing one character. So that is your output size, and that will depend on the task at hand. So for English, it may be that you are outputting the next character, so you will have a 56 dimensional softmax vector. And so in PyTorch, it is you, instead of softmax, you do something called as log softmax. So basically, you take the logarithm of the softmax, and that is just for making computations easier. Okay, so this is a very simple RNN model. So let us see uh, how how you do this. So earlier we saw that whenever we are trying to describe how a network, uh, given some input, how the network processes it, we have to learn, we have to write this forward function. So here we have written one more function called init hidden. So basically, how do you initialize the hidden inputs, right? So for weights, this is already taken care of when. So for weights, it is already taken care of whenever you create the model. The weights are initialized according to one of the initialization schemes that you have seen, like JPR or HC initialization or random initialization. But these hidden states that you have, it will not be uh, the initialization of the weights will not also lead to initialization of this. So that is why we have to write a separate init hidden function, which will say that okay, all of my hidden states are just initialized to 0. And as soon as I find get a new input, I will try to learn this initialization states as well. Or sorry, hidden states as well. So as you know, the input to RNN cell is the input itself, as well as the hidden state from, or the state space, or sorry, the state of the previous time step. So this function torch.get basically concatenates them. have the input vector, and you place the hidden vector just below the input vector. And now, as usual, you once you get this combined vector, you pass it through this I2H layer, which you have defined here. You get some output here, and again you pass this through the H2O layer that you defined here, and then you compute a softmax, or rather the log softmax of this. And again, the output that you get from here or is not just the output, the y that you get. You also have the output, the hidden state that you have, because that will again be passed to the input of the next step. So here the forward will output of the output variable as well as the hidden variable that you have. So this is a simple, very simple RNN. Now again, so for this example, we have defined the dimension of the hidden space or the state space as 128. So this thing is 128. So that means these combined vectors will be, let us say, 130 plus 128, something like 258. And we initialize our model here. Okay. So now suppose this is my input, right? Okay, let me run this. My model is created, it is loaded. It is not, I'm not using GPU, I'm just running some CPUs. Okay, so as an example, suppose I have this letter A. We know how to convert it into a tensor. So basically, you have to one hot encode it, uh, and you convert it to a torched up tensor. Hidden state as input to the RNN. That's a simple input. We're not doing anything else. You just get the and now again, suppose I have this word Albert, and so Albert is of size 6 cross 1 cross 57. That is, 6 comes from ALBERT. There are 6 letters. One is just each letter is of has 1 by 57 dimension. So 57, because there will be some additional character, like there might be like full stop, comma, and so on. So the and also okay, and also you have this uppercase and lowercase, so 26 plus 26. So therefore you have your vocabulary length is 57. So this Albert has a dimension of 6 cross 1 cross 57. And again, let me I pass this as input and get some garbage type of output from this. So okay, so this is just a sanity check that okay, my network is working at least. Now let us do this thing, bring this network. So before that, again, the labels that I have are the different countries, right? So like German, English, Italian, Chinese, and so on. So I have to, the network will not, or the system will not understand what those words are. So I have to categorize it, right? I have to say that, okay, zero is American or zero is English, one is German, two is Italian, and so on. So this uh, this function does that. So that means you have to say which number denotes which category. And again, because you want your model to be robust, you don't pass the same input each time. You just randomly create a training sample because there are hundreds, thousands of names. You don't want to, yeah, of course you can train on all of these, but instead of this, I'm saying that okay, let me just randomly take some name and then use that for training. Because you're not running it on GPU and this is not a complicated task, you don't need a lot of data. You can just randomly select some things and then just train on this. So these functions does that. So for example, from the Arabic category, I'm taking this word pata. From Scottish, I'm taking this word young, and so on. And now, okay, it we come to training. So here we are using something called as negative log likelihood loss. So you must say that we in classification we go for cross entropy type of loss. So this because we're taking the log softmax, not the softmax, but the log of the softmax. So this is compatible with the log softmax loss. So these are various types of loss functions you can use in combination with what type of output layer you have. So let us say I'm using this negative log likelihood loss, and these are my hyperparameters. So learning rate is say 0.005, and we run the training function. So first of all, I initialize the hidden states that I have. So I wrote this function init hidden before, and I set also this line sets all of the parameters or the gradients of all of the parameters to be zero, so that noise or garbage will not be added over. And then for the inputs, so this line tensor will contain your inputs, and I store all of the outputs that my RNN gives to this output comma hidden. And then because I know the category of each of these words, because I created that data set here, I created a data set here. So using the NLL loss, I just take the compute the loss and do back propagation to update the or compute the gradients. And then this line will just update the parameters, you gradient descent update. So this is my basic training algorithm. So uh, anywhere you any problem that you do, this will be the basic steps. So if you remember for CNN, we did not have this hidden thing, and we're using I think cross entropy type of loss. But here we are going for sequence to sequence or sequence learning models. So we also need to take care of the hidden vectors. So that those will be the only few changes that we want, but these things will remain same. Like you have to set your gradients to zero, you have to calculate the loss, you do the back propagation, and then they do the gradient descent update. Okay, so we are running this for say 10,000 epochs, and we want to print my information every 5,000 epochs. So, and now these are some uh, functions to calculate the time that has been spent. So let us run this. So here we are saying for some input whether we're correctly or we're classifying the name or incorrectly. So for example, here I have the name Norman, it is classifying as Irish, which is not correct. But here it is classifying it correctly. So these are just some examples. And now let us plot these. So, okay, my model is doing well. At least the loss is decreasing. If it was not decreasing, it might have been a problem, but okay, loss is decreasing. And now, uh, same as we wrote the training phase, we also have to test the results on the test data. So this is same as that. You just get the outputs. You don't need to do zero grade or backward. You just get the outputs and check whether the output match with your actual labels. And then we are also plotting confusion matrix here. So yeah, so this is the confusion matrix. So if you're not aware, confusion matrix basically says what is the correct number of predictions that you do. Say when you're in, so this is in the first line, it says that if your input is French, you are outputting French with this much, I mean, around 0.3 times. If your input is, say, let us say Japanese, and you are outputting Japanese is almost 0.8 times. So for if you have a good model, you want that this central diagonal line is as bright as possible. That means you are correctly classifying everything. So for this example, it is very bad. All of these are dark. That means you are not doing well. So only for, let us say, the Japanese language and maybe the Greek language, the model is classifying well. And even for, say, Arabic and Vietnamese, the model is classifying well. Other than that, the model is not classifying well. So this is a confusion matrix.
Hello, sorry to interrupt here. So this 0.8, it's higher probability, right?
Right, right.
That the output is correct. So the yellow means it's highly accurate and zero
Yeah,
means it's less accurate.
less accurate. So with 80% accuracy, you are get predicting Japanese and Greek, but the rest of them, the model is not able to do a good job on the rest of those.
Can I just see the table of contents in the right hand side?
This one,
That there are three lines, no, in the top below
this,
commands. In
yeah,
yeah, just a minute. Okay, yeah.
okay.
Thank you.
So, okay. So this was a simple network, and yeah, you can also give something on your own. It will output something. So I'll share this here. You can do these things, right? You can change the language probably if you have access to some other language data sets. You can use that. Or maybe, so this was a very simple recurrent neural network type of thing. In general, you don't need to create this. Uh, yeah, in general, you don't really need to create this linear I2H H2O thing. There are actually RNN. You can actually call the RNN function to create these layers for you. So you can. So those are all readily available in the PyTorch library, or you can use this complicated LSTM or GRU layers to get better results. So yeah, this was a simple task that we had. Yeah, any questions, anything else you want to discuss?
So, what is the accuracy of this model right now?
So okay, I think I have printed that previously. Yeah, I've not printed the accuracy right now, but it will not be good. I don't know. I have to, yeah, I've not wrote this up.
That
But
will
this
be
is,
average across all these classes, right? That
yeah, you
depends
have to
on.
add these up, all of these diagonals that you have. That is the true positives, and then divided by the number of examples that we.
Okay. And if I
So,
want to increase the accuracy, then what?
so if you want to increase the accuracy, there are a variety of things that you can do. You can increase the number of iterations. So that is one thing. You can change the learning rate. You can, so here I think we are just, yeah, using I think 10 examples or so. So instead of that, you can use, so let us say try 1,000, 100 or 1,000 examples. So the thing is, more the number of examples or more the number of data your model sees, the better it will perform. So let us see 1,000 examples. It will be slow, but your this line should be brighter this time. So it is same as if you see a lot of examples, you learn more about a subject. Right? So same as that. So here you see the loss. Earlier the loss was around 2 or something, but as I give more number of data, as I show the model more number of examples, the loss is much less. So here you see starts from a smaller amount of loss, and let us the results now. You see the diagonal is more brighter than the previous one. So let us say now increase the number of iterations. Yeah, it will be slow. Let us say it will do 30,000 times. Increase the amount of data, you increase the number of iterations. That means you are making your model more complicated by getting, because it is learning more and more. So the more you do that, you see more of these diagonal lines are lighting up. So which is good. Ideally, you want all of these to be close to one, which is all yellows.
So the number of samples for that specific class, can we
Hmm.
check that like for Japanese, how many samples are present in the dataset?
Yeah, we can check that probably. Uh, it's about 10 20 samples.
And automatically it will take care if there is bias towards higher class, in the
Yeah,
class having higher number. It is
yeah,
automatically taking care.
yeah, right. It's possible that some classes will be more. or some classes will be less. Okay, so here actually we have given them a category number, so we don't know how to do that. But so okay, this is just written an example. So this. Okay, we are not storing all of these at once. So you see, we're not storing all of this. So each time I'm calling a random training example, it will just call once. So here, yeah, it will call and it will pick up a random example, say Japanese this time, and let us how many times you see Japanese. So it's basically a mix. I mean, not you're not seeing just one. So say for some time there here you have Japanese, Scottish, Czech, Korean, and so on. So you're not just limited to just one thing.
Okay.
So you are calling the training example each time actually. So increasing the iteration means you are increasing the number of or amount of data that you are seeing. Yeah, I was yeah, I was thinking I stored all of this data at once, but that is not the case. So there is a good variety actually. Uh, Having variety is good because but see sometimes it is just uh, passing or using three English surnames at once. But it's still okay. Still the loss is going down. So these are just hyperparameters you have to try which works. You can change the learning rate, you can uh, yeah, increase number of iterations. And that would be try this one, you just save. So the reason we're not saving all of these at once is because each of these data, if you see, each data point is of size 6 cross 1 cross 57, which is around uh, 360, something less than 360 dimensions, which is large, right? And you have if you have 1,000 such dimensions, so it will be a large matrix. So instead of storing all of these at in one matrix or in one check, we are just calling its random training example at each iteration so that you don't need to store all of these. Okay, so yeah, anything else? So it would be good to go try this out. I think to get an example of how to design a network, to replace these I2H and H2O layers that we have. So yeah, instead of having just linear layers here in place of H2O and I2H, try to check out how you can insert a RNN block itself here, or how you can insert an LSTM or GRP block here, and try to play around with it. Uh, Also, there might be some other examples here. So, for example, there will be an example where they say how to understand the working of LSTMs. So it will be good to go through this. I'll share this in the shared drive. Any other questions?
So this notebook, is it possible to share it here in the chat?
Okay, so actually I'm not share this one. The copy and share. So I'll remove my directory, and if you want, you can use your directory there. I've commented where you need to keep that. So I've shared the link in the chat. You can go to the link, go to file, and then say save a copy in file, and you can make changes in that copy instead of this one, because this will be shared with everyone. We don't want everyone to be working on the same thing. Is the link accessible? Yeah, is the link accessible? I've shared it in the chat.
Yes, I can access it. Thank you.
Okay. Yeah, for people who are joining now, I have shared the link to notebook in the chat. So we went to the notebook a few minutes ago. So you can go through the notebook yourself, and there are certain exercises at the end. If you're interested, you can go through those exercises.